Hello, our project is Seizure Prediction. I'm Shruti and my team members are Elijah and John. Our project uses EEG readings and a convolutional neural network to produce a machine learning-based algorithm that can detect an epileptic seizure. The dataset is a collection of EEG readings taken from 22 subjects during their withdrawal from anti-seizure medication at Children's Hospital, Boston. 5 subjects were males ranging from ages 3 to 22, and 17 were females ranging from ages 1.5 to 19. There are 664 total EEG readings, 129 of which contain one or more seizure readings, creating about 50 GB of data. Each file contains an hour of data, which is made from 23 channels with a sampling rate of 256 MHz. Based on the research done by Ali Shoaib, we decided to split these samples into 5-second epochs, resulting in 720 sections of input per file.
Before we could feed this data into our model, we had to get it processed in a way we liked. The first option we tried was direct images of the EEG reading. This used a lot of pre-processing and drastically increased the size of our data, which was already very large. The second option we tried was to condense the full hour readings into a single spectrogram to save space. This also failed to work due to file typing issues. We finally settled on using MNE to convert the EEG readings into raw data types and then feed those into our model directly as NumPy arrays. We chose to use a convolutional neural network at the recommendation of our TA. From reading the research done by Ali Shoaib, we mimicked the way he fed his data into the system on a single patient basis. And from the second reference paper on deep learning, we chose to use temporal and spatial filters in our convolutional layers. We chose average pooling over max pooling since every single channel should increase during a seizure reading, and we wanted to rely on a complete increase over increasing in certain channels. We used ReLU activation since we discussed its advantages in class, and finally we used binary cross-entropy when training to make the final distinction of whether or not a 5-second window is seizure or not.
We had several conclusions from working and processing EEG data. We found that EEG readings are a very good predictor for stroke detection. Because of how distinct the data was, even when the model was trained on a single patient's data, it was able to produce accurate labelings and predictions. Another finding was that after using differing intervals over time for the model, we concluded that using 5-second intervals returned the most accurate results. 2 short intervals resulted in needless processing, whereas 2 long intervals for training the model resulted in loss of accuracy. One unfortunate result we got was that our model was overfitting for the test data. While the accuracy for the test data remained at a high 95%, the model loss near the end of the training reached up to 0.6. We think that using a wider, bigger set of data would have helped to solve this problem. Our project was a success, but we are looking forward to several improvements if given the time. First, to increase accuracy, we would like to utilize a greater data set as well as make our model able to train on multiple sets of data. We would also like to potentially work on real-time processing of EEG data for stroke detection so it can be utilized in real-life situations, such as at hospitals. The biggest stretch goal we are looking at doing is to train our model on the features of EEG data that are present before a patient has a stroke. Being able to preemptively warn someone when they're about to have a stroke could potentially save lives and would be a very useful example of using AI to help people. We are very excited about the prospects of where we can bring this project.